Okay, are we live? Light looks good, sound good. Excellent. Good morning, everyone. Exam day here at Chem 1 this evening at 6 or tomorrow morning at 6 a.m. Are the exam times. 99% of you tonight at 6, some international people tomorrow at 6 a.m. Today, I'm going to do talk just for 5 or 10 minutes, maybe 15 minutes about the last topic that will be on the midterm tonight. And as I warned you Thursday, there are a few questions on the exam about periodic trends. And I'm just going to go over them quickly and we all know what's on the exam. So I'm going to stop as soon as I won't say anything today that's not on the exam. So we'll stop as soon as I get through all that material. Couple things about the exam in general. So it's going to look a lot like the homework in the chem quizzes. If you've done all the homework and you've kind of reviewed the chem quizzes, you'll feel real comfortable on the exam. The exam is the same kind of format in that on many of the questions, there's a single graphic or a single table or chart or plot, and then there'll be 4 or 5 questions about that. What you can do is, or what I recommend you do is, it's okay to take a screenshot, say, of the static thing that you're going to use for the next 4 or 5 and put that in a separate window so you don't have to scroll up and down. On the previous exam, we put them all in a PDF for you, so you could have that PDF open. If you like that better, mention it to your TA. We did not do that this time, so we'll just ask you to take your own screenshot, or not if you feel confident enough. That's just some test-taking advice. We know that the Canvas, the B course testing system, is not the greatest, but that's what Berkeley is supporting, so that's what we're using. Today, we're also going to do something that we've never done before. Your UGSIs and I all got together yesterday afternoon, went through the entire exam, well, as best we could. There's actually there's thousands of possible versions of the exam because it pulls from databases, so you don't all see the same thing. But we went through the questions, made a lot of edits, and the GSIs had a lot of good suggestions, so that all looks good. The thing we're going to do today, which is new and just for fun, the TAs in the room and we have our bell, our dinger, and they will do a ding, and the UGSIs, Andrew is alerted the GSIs who are watching remotely, so that's Anji and Ben and Lillian. They can type ding literally into the chat. And when are we going to do that? They've all seen the exam, and we've looked at it for a long time. So when I say something that somebody says, oh my God, that is exactly what would help me do one of the exam questions. So if they see a statement that's particularly pertinent, they're going to hit their dinger. And if I think it's important too, I will hit my dinger, or I will respond with applause to their dinger or a comment. So listen for the dings, especially in this first 15 minutes, because this is the new stuff. Although I do, of course, did encourage you to look at this in advance for today. So what we have to talk about today are trends in properties. So we're going to talk about the elements in the periodic table and how trends in properties like ionization energy and electron affinity and radius and the effective nuclear charge follow trends. So say they will increase going across or increase going down the periodic table. And there's good reasons for why they do that, and you should understand why those trends exist and the general nature of the trend. So we'll start with a little reminder of last time. ionization energy and effective nuclear charge are trends on the periodic table. So we can back up a little bit. What I wanted to emphasize mostly is that when you have a one electron system, it's very easy to calculate the ionization energy because there's one electron in a nucleus. Simple. When you go to many electron systems, then we replace this actual charge on the nucleus, Z, with something we call the effective nuclear charge, Z effective. And you can still calculate the ionization energy from this, but usually it's done the first time the other way around. So you can measure ionization energies rather easily in the laboratory. The Z effective, the effective nuclear charge, isn't something that you generally measure. It's something that you calculate after you know the ionization energy. So you see how hard is it to pull off that electron. And that says, oh, well, there are only two parameters that I can mess with here in this ionization energy formula. One of them is the principal quantum level. The other is the charge on the nucleus. So if I have an atom that I'm ionizing from principal quantum level 2, I'm stuck with putting 2 there. I can measure the ionization energy and then calculate a charge, an effective charge. That is the charge that that electron must have felt as you pulled it away. So it's not a number that you can come up from a mathematical calculation in general. It's what we call an empirical number. Empirical means comes from observation or experimentation. So we do that empirically, and I think it's important for you to understand that. I'm never going to ask you the value, exact number of a Z effective, but I'm going to ask you to understand how it might change from system to system. So here we go. The many electron systems have this effective nuclear charge, and it's a catch-all kind of parameter. So it takes into account all what we call the shielding, all the electrons in the lower shells that are shielding the outermost electron. And it takes into account how far away it is. Of course, N, the principal quantum number, also takes some of that, how far away you are, into account. But everything basically, all the miscellaneous and varied conditions that might affect how much attraction there actually is just piled into this effective nuclear charge. And we saw that it was interesting, in particular, that when you ionize hydrogen, this is simple. This is one electron. So that electron in the one state sees the full +1 charge. When you ionize helium in the neutral ground state, so 2 electrons in the S, that is something slightly, as you can see, less than twice that. So more nuclear charges, Z is squared here. Effective nuclear charge is squared. So when you go from 2 pluses, from 1 plus to 2 plus, this number changes a lot, from 1 to 4. But going to the the first principal quantum level with that double charge, this number is still kind of near twice as big instead of 4 times as big. And that is because of the interaction between the other electron in that system. The cool thing we noticed is if you have excited state helium, 1s1, 2p1, so that electron is in the 2 shell now. So this is, N is also 2. Now what is Z effective? It looks, here's the ionization energy of excited state hydrogen, the hydrogen with the electron in the 2s shell, or the 2p, doesn't really matter for hydrogen. The ionization energy looks almost identical. So that told us that inner shell electrons, especially S electrons, are very good at shielding this outer electron. So there are 2 electrons here. There are the 2 pluses in the nucleus, But that electron out in the 2 looks exactly like hydrogen in the 2, where there's only 1 positive charge. So helium, that electron in the 2 is looking back at the nucleus. The 1s electron down there is shielding out almost 1 full positive charge. So the guy out here sees just 1 positive charge. So Z effective, we could calculate it, is 1 in that case. So that was interesting. That led to this whole idea where the energy is mainly of energy levels of atomic orbitals are mainly determined by n, the principal quantum level, but there's this small effect due to this shielding. So these 2p electrons, if you have 1s and 2s electrons, then they shield those p electrons, and these move up in energy. And you know, going up in energy is closer to ionization. Ionization is at the top of our energy chart. So they're getting closer to that, so they're easier to ionize. And the remarkable thing, and the thing to make most careful note of, was that the 3D is so affected, it becomes higher energy than the 4s. So that the 4s electrons enter the 4s as you're building them up before the 3D, because the 3D is, because of this shielding, slightly higher in energy. So I just wanted to show you this, a couple orbitals. Here is a, that's an F. I will change it. This is principal quantum level 3, and so this is n equal 3 and s orbital. So s means L equals 0. Okay. Now, you should have been able to tell me all that just by looking at it. Okay. You should have been able to say 3s. Why? Ring your bells. Because in this case, what are the colors telling you? Wherever it changes color, that's going from positive sign of the wave function to negative sign of the wave function. That's a node. So I change color once, twice, 2 nodes. If this, wherever it changes color, there's a node in between the colors. That's what the colors mean. On the exam, it's just going to be black and white, because that's all we have. So if you go from black to white, the sound of the wave function changed. So there are 2 radial nodes. It's spherically symmetric, so you kind of know it's an S anyway. The fact that there are 2 radial nodes, you can't see any angular nodes, means it's an S orbital. So this is a 3s. The total number of nodes, as you know, n minus 1 is the total nodes. There are 2 total nodes here, so n is 3, 1 bigger than that. Okay, so let's look at another one. That's the 3 principal quantum level 3. Let's look at 2. There's n equal 2, 1 radial node now. The change changes once. What if I do? Now I'm at 2p, and you should be able to tell me I'm at the 2p. Maybe you recognize the dumbbell shape. Maybe you recognize there's 1 angular node. So in this case, the node is here. And that angular node, it's the only node. So it's angular. Every angular node gives you 1 value of L. L is the number of angular nodes. So you count angular nodes, that's the value of L. 1 angular node, L is 1. L is 1 is what? P. There are no other nodes. So there's only one node total. So N is 2. Okay? I can identify these things formulaically. What if I go to 3p? What's going to happen? Let's make it a chem quiz. I'm going to write it on the board because we don't have it. I'm going to go to 3p now. What's going to happen? I will go to whiteboard because I want to look at it. So I'm going to go from the 2p to the 3p. I'm going to show you on the board. The question I have for you is, what will happen? A, we're going to get one more radial node. B, one more angular. Or C, no more nodes. Okay? So we're just going to have you ring in. So this is a quick one. Just we're just going to take 30 seconds. Guess or tell me what's going to happen when I go from the 2p to the 3p. A, I'm going to see one more radial node. B, I'm going to see one more angular node. C, I'm going to not see any more nodes. So let's see what you're thinking. 10 more seconds. And this, I just want to see what you're thinking. This is not, you're not going to discuss it or anything. Just tell me. Great. That's probably half of you. So let's see what the half of you are thinking. The half of you are thinking that A, I'm going to get one more radial node. A couple of you thinking, I'm glad hardly any are thinking C. I went from n equal 2 to 3. I get one more node. N is one bigger. There's got to be one more node. The question is it angular or radial? Well, L did not change. L is the number of radial nodes. Every p orbital there has one angular node because L equal 1 is p. So you're going to get one more node. What is it? It's radial because it can't be angular. Okay. There's an exact kind of exam question here. And here I'm going to make it really obvious. So I'm just going to change it from n equal 1 or 2. I'm just going to change to n equal 3. Boy, look at that. A radial node appeared. Now there's a radial node. See the sign changing color here? And the sign changes color here. Plus to minus to plus. Plus to minus to plus to minus. A radial node and an angular node. That's the 3p. It looks different than the 2p, and you can tell it's a 3p because of that radial node. Yes. I hear a bell ringing. Good. That helps one of your UGSIs answer a question on the exam. Okay, here's the periodic table again. We recognize now the structure of the periodic table comes from the values of n. N gives us the rows. What gives us the columns? L gives us the columns. L says there is one value of S, so I can have one value of M sub L for this value of L equals 0, and 2 electrons. So bing, bing, 2 columns. Here, I have 1, 2, 3, 4, 5, 6 elements. And that's because L is 1, M sub L has 3 values, and each value can hold 2 electrons. So the fact that M sub L is 3, L is 1, I say L dominates because L fixes what M sub L can be. Okay, so we see what we call the S block, the P block. Isn't that exactly a question on the exam? I saw it. Did you guys? I maybe know them better because I wrote them, but they saw them too. The S block, the P block. Is anybody dinging? Do I see any dings in the live stream? Angie and Ben and Lillian. And then there's a D block, L equals 2, and then there's the F block, L equals 3. Give us the columns. So the rows and columns come directly from the quantum numbers. So let's just tell you straight out. Atomic radius. You would expect the atomic radius to increase as n gets bigger, and it absolutely does. You would expect, though, that the charge on the nucleus getting more positive would pull the electrons more closely together. Those two things both happen, okay? So more charge on the nucleus would tend to get you smaller radii, smaller elements, but larger quantum numbers give you larger radii. So it's basically a battle, and that's where Z effective comes in. Z effective says, well, I'm out there in n equal 4, but what kind of n equal 4? How much charge is that n equal 4 seeing? How good is the shielding? If I have really good shielding, then that n equal 4 can be big because I don't have a lot of effective nuclear charge. If I have very good shielding, then that n equal 4 might be smaller because you're seeing charges and you're drawing the electrons in. So those two things battle, but you can see what wins. As you go down a column in the periodic table, so these are increasing radii, you can see it increases as you go down a column. And as you go down a column, you're making Z bigger fast. You're going down, so going across, you increase Z by 1. But going down, you increase Z by a whole shell. But you're going to a new shell. You're going out to from n equal 2 to n equal 3 to n equal 4. And you can see that is the effect that kind of wins. So just going to that next principal quantum level, even though there are more pluses in the nucleus, you're also adding 10 more electrons for those 10 more plus charges. And that's really doing some good job at shielding. And the principal quantum level 4 is farther out, 4s, 3s, 2s. You see that as you go down a row. Down a column. As you go across, look at that, the radii decrease. So things get smaller as you go across. And that should be now, I hope, more obvious to you because you say, well, now the charge is increasing, but n isn't. You're in the same principal quantum level all the way across, but you're adding more charge. So as you add charge and you add another electron as well, but it's in the same principal quantum level. So it experiences the same kind of shielding, great shielding from the inner ones. The more charge kind of wins, and the radii gets smaller. Now that's going to link directly to the trend in ionization energy. And I'll just tell you before we look here, that should, in your mind, link directly. What's one of the things that's going to tell me how high the ionization energy is? Well, what the radius is. If I get closer to that plus charge, I get further down the potential energy well. That's harder to ionize. Here's big radius. As I go to smaller radius, I go to those lower energy states, harder to ionize. So radius, ionization energy, effective nuclear charge, all intertwined. Let's define, we've already defined this many times, we'll do it again here now. So ionization energy and electron affinity are complementary in that ionization energy is removing an electron. How much energy does it take to remove an electron from a species? So I go to one more positive charge and a free electron. Electron affinity is you add an electron to something. So this is out here, a free electron. What's the energy change when I force that electron on there? You might be surprised that it often is lower energy. Energy is almost always released when you add an electron. That is lithium. Is that a good example? Now, yeah, I think lithium's okay. Lithium, you add an electron. We'll have a chart in a minute. You add an electron, and the Li minus energy is released. So this is exothermic. So Li minus, a lot of dings going on there. Li minus is a lower energy state, believe it or not, than Li neutral, because that ionization energy is negative. These are that electron affinity, sorry. Ionization energies are all positive. It always takes energy to remove an electron. So here are some numbers. Just for your edification. We've already seen a little of this. So remember, we took the alkali metals, sodium, potassium, rubidium, francium, and threw them in water. We did that. We showed that demo. And when you threw them in water, the explosions kept getting bigger as you went down the column in the periodic table. They kept getting bigger because the ionization energy is lower. So you're saying, how much energy is released? Well, I have to ionize, so I have to put this much in, but other things are being formed, and they're releasing, and you form by and large the same stuff. So if it costs you less energy to make the ion, same stuff is being formed, and that releases energy, then you get more overall energy released. Here's some electron affinities, and you notice, look at this, chlorine, Cl minus, very much more stable, lower and down the hill than Cl, the atom. But there's a ding on that. But sodium also, so sodium minus, a little bit lower down the hill. We'll look at that a little more in a minute. First, let's look at why these explosions are bigger. And I'm just going to write this really kind of fast. I said it in words. I'm just going to say it or write out the equation. What I said in words was this, the ionization part always happens. So ionized sodium, rubidium, francium, potassium, whichever one. The M is that thing. That happens. But this is the reaction that's releasing all the energy. So you have to add those two to get the total energy. And so this is always the same. If this is getting smaller, it takes less energy putting in here, you're getting the same out. Then the lower the ionization energy, the more energy comes out. So that's why the explosions get bigger when the alkali metals, sodium, potassium, rubidium, francium, as you're going down the periodic table, the explosions get bigger. Redox reaction, we'll come back to that later in the class. It's the last thing we cover, I think. So here's the trend in ionization energies, and this should make some sense now as well. So easier to ionize as I go down the periodic table, and we kind of understand that now. We're going to a very much bigger radius. You've got all those electrons in there. So even though francium, there's all those charges at cesium, all those plus charges, you're getting quite far away, and those inner electrons are good shielders, easier to ionize. Z effective is getting smaller. Okay, the effective nuclear charge on the outermost electron must be smaller if it's easier to ionize. Those two things are linked together. The other thing occurs as you go across the rows. Now, you said the opposite thing happened. Those were getting smaller. And indeed, the ionization energies get bigger. Okay, more tightly held because of now mostly it's the radius factor. You're coming in closer. Z effective is getting bigger as you go across. Ionization energy is getting higher. Okay, so this is all relatively straightforward things to think of just in terms of N, the size, the charge on the nucleus. Okay, let's do a chem quiz then. What is the ionization energy of Cl minus? So ionization energy, Cl minus. Here it is, Cl minus going to Cl and an electron. How much energy does that take? A, B, or C? Think about that for a minute in your small groups. The thing's still running, so I'll stop it. Start it again. Okay, you have a screenshot saved of that now. Talk about that for a minute, and we'll take a vote. Okay, let's come back together. Push a button if you have not so far. We'll see what you're thinking. Most of us, 46%, just under half of us think C. They think that this reaction, this is positive. So they think that's endothermic, that I have to add energy to do that. And somehow they've even come up with a number. It's the only endothermic one. So if you think it's endothermic, you would have guessed that. Would you think it's endothermic? Well, it's an ionization, and I said ionizations are always endothermic, so I guess you could have got that straight away. But here's something clever. Here's how you write ionization energies. You're taking X and you go to X plus and a free electron. Here's how you write electron affinities, taking something and adding an electron to get X minus. But here's what you might have noticed. This reaction that's the reaction we're asking about. Cl minus removing an electron. So that reaction is the reverse of that reaction. So not only do I know that that's endothermic, I know it's the opposite of the electron affinity. So you can see electron affinity is minus 349. Well, going in the other direction, you got to put in 349 kilojoules per mole to do that. Okay? Shouldn't we be hearing just a cacophony of dings to do that? So here's just a summary, and I've correlated it with electronic configuration here now. And I think that's important because it gives us another conceptual thing to grab onto. Here's hydrogen. 1s is its electron configuration. We've looked at its ionization energy many times, but adding electron is favorable to hydrogen. Helium, 1s2, we looked at that ionization energy, but look at this. Adding an electron to helium is not favorable. Okay, interesting. Let's continue and see how that trend continues. Lithium is now it's in the 2 principal quantum shell, shielded very well by these 2 electrons. So look what happens. Even though this has an extra charge and the charge is squared in the ionization energy equation. So you go from 4 to 9, 2 squared to 3 squared. Much bigger in Z. The ionization energy actually decreases. It's easier to ionize lithium because of the effective shielding. So this guy out here is seeing, in fact, if you scratch your head, you could come back and see how much effective charge is it seeing. It's seeing a little more than 1. How do I know that? I know that because I remember in that last slide when we ionized hydrogen from the 2s, when we ionized hydrogen from the 2s, that was 328 kilojoules to do that. It takes just a little bit more for lithium in the 2s. So it sees just a little bit more than plus a full charge, even though there are 3 full charges down there. Okay. Here's beryllium now. Beryllium, 1s2, 2s2, a little harder to ionize it, not going up by the square root, but by the square of the charge, but going up. But look again. Beryllium says, no, this electron affinity, this adding an electron is not favorable. That's interesting. Here, I'm going to go to boron. Now I'm putting an electron in the 2p, but look at that. That has a lower effective nuclear charge than this guy because those s electrons shield the p better than they shield kind of each other. So these are all s electrons, but they shield the p's quite well. They don't shield each other as well. But you can add an electron. It's favorable to add an electron to boron. Electron affinity is negative. And you can continue down here. We'll stop at a few places. Nitrogen has 2p3. Its electron affinity, it doesn't necessarily want an electron. That's not a lower energy state. And look at this, fluorine tremendously high electron affinity. Fluorine atoms go to very much lower energy when they accept electrons. So F minus is downhill. That would be, F minus would be the same electron configuration as neon. So that's a good thing to realize. But look, neon, again, electron affinity about 0. Doesn't want to take another one. So where did that happen? Let's just draw a little picture here. The ones that had this small electron affinity, where are those? Well, you had a small electron affinity here at 1s2, in fact, a horrible electron affinity, unfavorable. Here at 2s2, you had a small electron affinity at 2p3, and you had this small electron affinity at 2p6. So what is that telling you? That's telling you that, let's draw, this is a great exam question. It's not on this exam, but it'll be on the final. Here's the exam question. There's hydrogen in the, let's not do hydrogen, let's do beryllium, 1s2, 2s2. I would write, I'll go to the board here, go to the whiteboard so we can do it easily. So beryllium, 1s2, 2s, 2s2. I have the ionization energy, something like 800, I forget what it was, 500, is that what it was? 500 kilojoules per mole or something like that? No, I think it was 800. 800-ish or 1,000-ish. The electron affinity is, don't tell you what it is, but it's positive. So if I were to draw on the board 3 energy states, 1, 2, 3, and ask you to label them beryllium, beryllium plus, and beryllium minus, you should be able to put them on there. And you should get some insight out of it. Where do you put them? Beryllium, well, I know beryllium has to be lower energy than beryllium plus an electron. The ionization energy, Be goes to Be plus a free electron. That is exothermic. So that means that guy is above that guy. B minus compared to this. So beryllium plus an electron going to B minus, that's the electron affinity. That is endothermic. So beryllium lower energy than this. So B plus is the highest, then B minus. So I'm sorry. B is lower than B minus in energy, and B is lower in energy than B plus. Because of that reaction, this is exothermic. So what you see is when you're just at beryllium, 2s, you don't want to ionize. It takes energy to ionize, but it also takes energy to add an electron. So beryllium is here, then beryllium plus and beryllium minus. This 1s1, 2s, or 1s2, 2s2, that is the lowest energy state for beryllium. If you compare it to having one more electron or one less electron, so compare it to 2p1 or 2s1, that's one more electron, that's one less electron. Both of those are higher in energy. So there's a dip in free energy Hill right at 2s2, the filled principal quantum level 2s2 there. And that's what happens on all of those. When you fill a principal quantum level, you get to that dip in energy. Those are the lower energy states. So you see that, maybe you had this chemistry before, and if people say a full quantum shell is stable, stable means squat shit. What stable means is going anywhere else costs you energy. That's what we're seeing. Going elsewhere from here costs you energy. So naturally, you stay there. Oh, yeah, sorry. These are both endo for that. Thank you. The point is they're both delta H for both of those is positive. Leaving this state and going to the other state is not favorable. That puts beryllium at the bottom here. Okay, it doesn't change from boron to beryllium. Okay, yes, thank you for catching that. The whole idea is everything is endothermic to leave this state. That puts it at the bottom, and that explains what you might have heard in high school or your previous chemistry classes, that that's stable. I don't like to use that word. What that is the lowest local minimum in the enthalpy landscape. So it just lands there. Hard to get away from it is what we would say. It takes energy to get away from it rather than saying it was stable. Oops. Wrong button. Sorry. Okay, so that is it for the exam material. I'm just going to show you a chart because so this is still exam material, it's still ionization energy. Here is the trend in ionization energies, and now we can kind of explain this trend in ionization energies. So here it is. I'm going across a row in a periodic table from lithium to neon. I'm going across that row, and ionization energy is increasing. Same principal quantum level, more charge on the nucleus. It goes up in energy. Oh goodness, getting ding for that. Yes. So you could even explain these little dips in the energy between 2s2 and 2p. So in general, it goes up, but there are little dips in the energy. And you saw where they are. They're at nitrogen and beryllium. So you understand why that is. That was the 2s stable state, and this was the 2p3 stable state. It takes a little bit of energy to add an electron to the nitrogen. So half-filled 2p3 also is lower in the enthalpy landscape slightly. So you can figure these out by looking at the ionization energies and electron affinities. Okay, complementary things. And in our early chemistry classes, maybe it's easier to say, well, those are just stable. Half full shell is stable, full shell is stable. But you're beyond that. You're here at Berkeley. You can compare electron affinities and ionization energies and tell me that's the lower energy state. You don't have to do this magical stability thing. Okay, wonderful. Okay, which of the following has the smallest atomic radius? We'll talk through this. So atomic radius, we had to compare chlorine, argon, and potassium. And I think that trend should be pretty obvious, that you have the argon, 3p6, you went across the row of the periodic table. It got bigger from chlorine to argon. You went down to potassium, and you atomic radius decreased So you have argon, you can work that out from your periodic trends, is the going across there, has a smaller radius. Can I show the quick picture of that? There it is. So chlorine, argon, you got smaller, but then you went down one to potassium and it got bigger again. So 4s, that's the bigger shell. Chlorine, the periodic trend is get smaller radius going across, and then going down one principal quantum level to 4, you got big again. Okay. So which of the following has the lowest ionization energy? Now, let's talk about this one briefly in our groups. I'm not gonna talk. Let's just talk through them because we want to get through some stuff. I'll talk through them for you since this is kind of this is all now starting to review stuff. Where'd my water bottle go? Oh, there it is. Sorry, didn't mean to walk out of frame. So I'm going to compare things. These are interesting species. Chlorine with 1-, potassium missing an electron. Chlorine you added an electron to. Argon is the neutral atom. So how do those compare in ionization energy? Well, here's something interesting. You add one electron to argon. Excuse me, you add one electron to chlorine, and you have these 8 principal quantum level 3, 8 electrons. Argon, 8 electrons in that principal quantum level 3. And potassium, you take away that 4s electron, and you're back down to the 3p. So these are what we call isoelectronic. These species all have the same number of electrons. And look at that. There's 3 electron configurations there. If I covered up these, you can't tell what element that is, can you? Yes, ding your freaking bells. That does not tell you what the element is, the electron configuration. Those are 3 different elements. They have the same electron configuration, so they have different properties. Chlorine, you added an electron to. Potassium, you removed an electron to. So the question was apparently the lowest ionization energy. So the lowest ionization energy is chlorine minus, and we can even rationalize that in a lot of ways. Chlorine, you know, you've added an electron to it, so it's already negatively charged. So it also got quite a bit bigger. You put a negative charge in there. That expanded, so you got a bigger radius on that ion. And argon is just a neutral atom. Potassium, you took an electron away, and it would contract in radius. Now the nuclear charge is bigger than all the electrons. So this one got effectively harder to ionize, much harder to ionize. This one got slightly easier to ionize. Argon in the middle. Okay, let's do a few calculations and other things to review. So now we're just full into all on review for the exam. What wavelength radiation is emitted going from n equal 3 to n equal 2 in a hydrogen atom, but assuming the hydrogen atom behaves like a particle in a box. So you could say, oh, let's say the box is 150 picometers long, and rather than treating it like the 3-dimensional quantum mechanics, we're going to treat it like 1-dimensional quantum mechanics. Let's say the electron is trapped in a box of about the size of a hydrogen atom. Can you do the calculation? Of course you can. This is a straightforward calculation. The energy levels for a particle in a box is on your equation sheet. And I should say this, your equation sheet, there's a link to it on the top of the exam. There's links to it on the syllabus, but right there on the exam, there's a link to the equation sheet. Click it, download the PDF, or view it. You have to use those equations, and importantly, you have to use those physical constants. You have to use the value of R and the value of C and the value of N on the equation sheet. This exam is slightly different in that there are a couple questions where you calculate a number and you enter a number rather than multiple choice. So if you're going to enter a number, you have to use exactly the same constants that we used when we did it, and we used the equations, the exact numbers on the equation sheet. So we can do this. We can look up the mass of the electron. We told us the dimensions of the box, 150 picometers. We were given two values of n, final minus initial. It's an emission, so 2 minus 1 or 2 minus 3, final state minus initial state. H is a constant, so we can just fill in all these values. So here's the value of H, Planck's constant squared. Here's the value of the mass of an electron in kilograms. Whenever you put a mass in, it has to be kilograms. Whenever you put a length in, it has to be meters. Whenever you put a time in, it has to be seconds. So don't put a mass in grams. If you want joules for your answer, don't put a mass in grams in, okay? And joules has kilograms in it. So joules assumes there's kilograms. So kilograms, meters, and seconds. We use the KMS system. So you just put all those numbers in. Here's the length of the box. Notice I put the length of the box in meters. So 10 to the minus 12, 150 times 10 to the 20 12, that's a picometer. I put the mass in kilograms and do that. And then final minus initial state. Actually, it was an emission, emitted. So final minus initial. The final state is 2. The initial is 3. So that number is, do that calculation. All that does is change the sign. You do that calculation, and you get 10 to the minus 17th joules. Okay? Convert that to megajoules. Convert that to joules per mole. Say it was a mole of hydrogen atoms. Mole of hydrogen atoms, you multiply that by Avogadro's number. Okay? On the exam, we ask you to do this kind of thing for a mole rather than a single atom. Okay? So that is the emission. It'd be interesting, convert that to wavelength. Do I do that? Yes. Convert that to wavelength. That wavelength is, this is an energy, so hc over lambda gives me a wavelength. There's my h, the speed of light, and my energy. So that is 14 times 10 to the minus 14, around 15 nanometers is the light that would be emitted, going from 3 to 2. We actually know 3 to 2 is not in the nanometer range. I'm sorry, tens of nanometers. It's hundreds of nanometers. We got this idea that that's in the visible spectrum, these transitions in an actual hydrogen atom. So the particle in the box is not that great a model. We're just doing this thought experiment. Not that great a model. The actual number, maybe I even put the actual number. The actual number is 650 nanometers for that transition. So it's right smack in the visible range. You got a nice orangey glow coming off of that. Okay, so The particle box, not very good. The actual quantum mechanical and measured value, 656 nanometers. So we talked about that electromagnetic spectrum, and there are the orangey glow of that 650 nanometer photon from hydrogen. Here's the range of the electromagnetic spectrum. We talked about the particle nature of light. That is the photoelectric effect. So, and we saw that electrons are emitted if you give photons with greater energy than this much. That's the potential energy you have to give them. If you have a photon of energy bigger than this, all this energy is kinetic, and you can plot that. It's linear. More energy after you get out of the well, then everything else is gravy. Everything else is kinetic energy. Okay? If you know this photon energy, that is the potential energy, the energy that just barely brings it to the top, but you don't get any kinetic energy. That energy there is the work function. So you can convert that frequency to joules and get the work function for that metal. Any energy more than that goes into kinetic energy. I'll say that again. You could connect that directly to, yeah. Everybody needs to stay awake. Would that help you on the exam? Mm-hmm. So for which wavelength in nanometers will an ejected electron have a kinetic energy 2 times bigger than the 300 nanometer emission? So here, 300 nanometers. Now be careful. I'm plotting this in energy, but giving you a wavelength. I think that's how I do it on the exam. It's plotted in energy, but that's what I do. I give a wavelength. Yeah. So be careful. I'm giving you wavelengths. You can still put them on the energy scale. E equals hc over lambda. So you know where they are, but it is a wavelength. So which has, what do I want to do? 2 times, we're going to talk through it. How do I get to twice the kinetic energy? Well, to get to twice the kinetic energy, this is linear. The slope is h. So how do I get to twice that? That is, here I've doubled the kinetic energy. What is that? Photon energy is what we want to know. You can do that calculation. So this is your first photon. You can tick it off by the marks. This energy is 1.5 times that energy. So you could actually do it on the scale. On the exam, I don't give you a scale and you have to look at it. I give you the numbers along here. So we could have either given you the number or you can just see it from the scale. So that photon energy is 1.5 times bigger. The wavelength then has to increase. Sorry, the wavelength has to decrease by that factor. That's a higher energy photon. Wavelength is decreasing as I go out there, but you know the multiple in energy, so you can calculate the multiple in wavelength. So the wavelength decreases by 2/3. This is a 200 nanometer wavelength. Okay, that's how it looks. That's how it looks on the exam. 200 nanometers there, 300 there is how it looks on the exam. Not those numbers, but just so you're comfortable. So which combination? Oh, we've done this already. So this is which combination of metal. I'll go back because that's kind of important. We'll not go through this quite so fast. Different compounds have different lines there. So because they have different work functions, and the kinetic energy you get is those work functions minus the energy of, so you take the energy of the photon you put in, subtract away the work function, subtract the potential energy away, and you get points on these lines. So in general, the higher the frequency of your photon, the more kinetic energy you get for a given metal. If you change the metal, then you might have a higher work function, a higher potential energy. So that's going to change how much kinetic energy you have. So this one we did in class. So we said that has the largest kinetic energy, even though this is a higher energy photon out here. We said that blue photon is hitting this metal, not this metal. If this blue photon were hitting this metal, you'd have to take that line. If this guy were hitting this metal, then you'd have to take that blue line all the way up here to wherever that line goes, and you'd get this kinetic energy way up here. Okay? Okay. For a metal with the photoelectric effect shown, will green light eject an electron? So these are the red wavelengths. Those are the blue wavelengths. Will green eject an electron? I think you can tell that you need more information. You don't know where green is. You know it's between red and blue, but not where it is. So yeah, there's not enough information there to tell you what's going on. You need to know the frequency exactly. I can't just give you any old frequency. That is absolutely on there, right? Because I just reworded it this morning to make it absolutely clear. Okay, so through which filter does a green solution appear black? Black means no visible wavelengths are hitting you. So black means you have to absorb every visible wavelength. Oh, well, I'm sorry. You don't have to absorb every visible wavelength, but you have a green solution sitting here, but you're looking at it. You put a filter in and it appears black. So green was hitting you in the eyeball. You got to put something in there that absorbs that green so that you see black. You don't see any light coming out. So you have to put something in the way that absorbs the green coming from that solution. So B here absorbs all of the green from the blue to the yellow. Oops. Oh, shoot. Oh, no. I hope that I don't have all this stuff in different orders. The answer to that one didn't appear. I think I have an editing error in the slides, but the answer to that one was B, that you have to put a green absorbing filter. And then this one we already saw, and I'm distressed because now we're having this one. I hope the solution to this one follows this one. So which transition here, so I've given you this energy level and I've given you a scale. So you can kind of read off the relative energies from the scale. I don't do that on the exam. I give you the numbers, but you can do it on this scale. You can see there's that 3:2 ratio again. So which transition does the absorption of 400 nanometer light correspond to if you know that this 400 comes in and that 600 goes out? So the 400 comes in there, the 600 goes out there, and then you know the ratio of them. And you can see in order to get this ratio of 400 to 600 in wavelength, you have to have this ratio 3:1 in N. And hopefully I do some calculations. Good. So here it is in calculation. You can see that wavelength drops by a factor of 2/3. That means the energy had to go up by 3/2, as we saw in the last chem quiz. So that has to go up by 3/2 because the wavelength went down by 2/3. So the 3-to-1 is the 400 nanometer transition, and the 2-to-1 is the 600 nanometer transition. 400 is the 3-to-1. So you can back that out from the ratio of those. On the exam, we don't give you the ratios, but on the exam, you get these as a multiple of R. So you could have seen the multiple that is 3/2 R, and that is 2/3 R. You could have got that same kind of result with the numbers instead of the graph. Okay, we talked about absorption and emission. We just looked at that one. That one was slightly different. So quantum numbers, talked about that a bunch, and we did it all this morning as well. We talked about diffraction and interference. Which atom is depicted by the figure? We've already done this a couple times. There's a radially symmetric, a spherically symmetric orbital with 2 radial nodes. Those are the only nodes in the picture, and there's 2 of them. So n has to be 3, one more than the total number of nodes. There are 0 angular nodes. So L is 0. So that is a 3s. Which one of those has 3s? So spherical symmetry, 2 radial nodes means it's a 3s. Look at the periodic table and see which has 3s. That's magnesium. Okay. Pretty straightforward there. You do that a half dozen times on the exam. Which set of 4 quantum numbers are allowed? So can I have, so I'm doing N, L, M sub L, M sub S. That's always how we do it. N, L, M sub L, M sub S. M sub S is +1 minus a half. So can I have these combinations is the question. N, L, M sub L, M sub S. And you know the restrictions. The restrictions are N determines how big L can be. L can be only as big as N minus 1. And L determines how big M sub L can be. M sub L goes from minus L to plus L in integer steps. So these are the rules. M sub S can be +1/2 or -1/2. Only 2 values for that. So where do we go here? You can probably spot pretty quickly the one that breaks the rules. I'm flashing them for some reason. That has, why am I circling that? Oh, well, that's a violation there. So here, let me get some writing here. L is 0. M sub L can't be -1. Okay, so that one's out. L0, M sub L can only be 0. That's an S orbital. That one's out. This one, I have an L equal 4 and an N equal 4. Can't do that. That's not allowed. If the biggest L can be is N minus 1. So the biggest L could be there is 3 in the 4th principal quantum level. So those 2 aren't allowed. What's the electronic configuration of rubidium and the quantum numbers? So rubidium, you look it up, it has 37 electrons. As you can ding a bell for that. 37 electrons. You have to put in the 37 electrons. And you may have seen this. I didn't do this in lecture yet, but you might have seen this picture. Hopefully you saw this picture in doing your homework. If you write out the principal quantum levels and L levels like this, then the order that the electrons fill, the order of the Aufbau order, the order of increasing energy, you can find by writing these diagonal lines. So I'm going to write the diagonal lines on there, and then we'll chant them out together. So 1s gets filled, then the 2s, then the 2p, then the 3s. So 1s, 2s, 2p, 3s, 3p, 4s before the 3d, and then the 3d, the 4p, and the 5s. Okay, so that's a little mnemonic. Did you guys, anybody show this in any discussions or anything? It's in the reading. I'm pretty sure the picture I took in the reading, and you can keep doing that. So this is a good thing, a good chart, a very quick way that you can predict and remember the Aufbau order of orbital filling. So I just got to go up to 37. So it takes a while. 1s2, 2s2. Okay, the electron count is going to run here. 2p, I can go all the way to 6 electrons there. It gets me up to 10. But then I got to go to the 3s. I can put 2 more in. And then I go to the 3p, and I can put 6 more in, and I get to 18. Then I put 2 in the 4s, and I get to 20. And then I go out to the 3d. Finally, I can put 10 in at a time. 3d, I put 10 electrons in the 3d. I'm up to 30. I only need 7 more. I can only put 6 in the 4p. So I need 1 more in the 5s. Okay? Should be able to do that very well. Summer, as you know, just sucks. There's no way. I mean, summer is just, there's things come up you too fast. In the fall semester, you would have done this 100 times already, and you would have had time to breathe in between the times you did them. You don't have any of that. I might even just stop teaching the summer session because it's not even fair, really, how fast this stuff comes. It's not a valuable learning experience to go this fast. So in protests, I might just stop doing this altogether. So the quantum numbers of the outermost electron, is that what I asked for? The quantum numbers of the outermost electron are n equals 5, L equals 0, M sub L also 0, and M sub S plus or minus 1/2. You can't tell. Okay, so you can write those all out if you want. Do I do it? Yes. N is 5, L, it's an s orbital, so L must be 0. M sub L has to be 0 then, and M sub S can be plus 1/2 or minus 1/2. Doesn't matter. Okay. Talked a lot about energies of transitions. We're going quite fast here, but you guys can replay this today. The exam isn't until 6, so you can replay this and look through it. So can a photon of 30 nanometers ionize helium plus from its ground state? If I tell you that from 1 to 2 is 120 nanometer transition, is that enough information? This is for hydrogen, so you have to be careful. If I'm going to ask you about helium plus, so helium plus, there's a factor of 4 on top of all those because it's a z squared. Z is 2. Got to multiply all of these numbers by 4. Every single energy level multiplied by 4 to compare helium to hydrogen. So in hydrogen, that's 3/4 R. And 3/4 R, the 30 nanometers is about 4 times that. So 4 times the energy, that means that has a 30 nanometer photon has an energy of about 3 Rydbergs. A 120 nanometer photon has an energy of about 3/4 of a Rydberg. That factor of 4 coming from the ratio of that photon to that photon. That photon has 4 times the energy of that photon. Okay? So that gives you an idea of the energy of a 30 nanometer photon. But what's the ionization energy of helium plus from the ground state? Well, helium plus, these numbers here are for hydrogen. So these are all z squared minus z squared over n squared times r are all these numbers. But for hydrogen, it's 1, because Z is 1 over n squared times R infinity. And you recognize that. When n is 1, it's 1. When n is 2, it's a quarter. Okay? For helium, it's still Z squared over n squared times the Rydberg constant, but it's the ionization energy, so we could say, don't even need that minus. But now Z is 2. So now it's 4 over n squared times R infinity. So the difference is a factor of 4 between the two. So you would have to put, for helium, you'd have to put a 4 there, multiply that by 4, and you get a Rydberg there. The point is, you're all the way down here at minus 4 Rydbergs. Is 3 Rydbergs in energy enough to ionize it? Nope. 3 Rydbergs would get you from 1 to 2. 1 Rydberg to from between 1 and 4 Rydbergs. 30 nanometers will not ionize He+. Okay, what's the wavelength emitted by hydrogen undergoing this transition? This I don't know that we have to work through. The wavelength emitted by hydrogen atoms, we just did 3 to 2, assuming it was a particle in a box. Here's 4 to 2, assuming the right relationship of the energy levels. So you can go through that calculation. Here I just put R in frequency units just to make the math easy. You can put R in frequency units if you want. That gives you frequency, and that makes it easy to go right to wavelength, which is what you ask for. So there are the calculations, 446 nanometers. So I calculate delta E from the difference, final minus initial. I did it with R in the value of hertz. You could put joules in there, but if you put joules in there, then you have to, well, just keep track of joules when you get here. Here, I just have to compute a frequency to a wavelength. If I had to convert an energy to a wavelength, it would just be slightly different relationship. H would come back in there. Okay? Pretty straightforward. Goodness gracious, there's a million of these. But that's fair, because there might be like 6 questions on the exam that have that picture. So I think there's 34 questions on the midterm. After there's 30. There's going to be 34. They're going to be between. There's 34. They're around 35 by the time we're done. I'm going to add one that they haven't seen tonight or today. Okay, this is interesting because it allows you to compare the effective nuclear charges. So I'm going to ionize these 3 states. I can say helium in the 1s2 a little. What is the effective charge? Is that harder or easier to ionize? Well, the effective charge, we don't know where it is, but it's between 1 and 2. And this one, we said, when you're in helium 1s2, 2p1, we said that 1s electron is very good at shielding that 2p. So Z effective is actually very close to 1. And here, Z effective is obvious. It's not Z effective, it is Z, because there are no other electrons. Helium plus in the 2s state. So all you're comparing slightly different situations, 3 different Z effectives, and 2 different quantum shells, n equal 2 for those 2, and n equal 1 for there. So you can go through that and plot that out, but there are all the relationships between those various species. And so you should be able to plot, you should be able to draw, once you know the ionization energies, where are the ionization energies? Right here, that's an ionization energy, that's an ionization energy. Work function, ionization energy, same thing. Okay. Don't break the bell, Leo. Leo's excited. Things are so cold in Canada. Everything is exciting when you come. Okay. Which of the following ions has the most negative electron affinity? So we said electron affinities are usually negative. That is, you usually release energy when you add an electron to something. So the question is, which of these is that the biggest? And that's there. I'm just showing you the electron affinity is the reverse of the ionization energy. So you can look at ionization energies for the atoms, and you can say the periodic trend goes chlorine, then a bigger ionization energy, then over to potassium, back down. Opposite of the radius. Radius is getting smaller and then bigger. So if you plotted radius there in a different color, the radius does the opposite thing. Starts here, gets a little smaller, and then gets bigger. Z effective, you should be able to plot. If you know the ionization energy, you know the effective nuclear charge with the quantum state. So argon in the plus state has the most negative electron affinity because it had this neutral state had the highest ionization energy. So it's another one of those cases where we're just looking at the reverse of the ionization energy to deduce the electron affinity. So those things go back and forth. Okay. All right, we're pretty much at the end of our time. So we'll stop here. I'll hang out for a question or two if there's some very pressing question. Don't ask me a question about, it has to be science. If you have a question about something else, email us. But is there any science question that I can answer right now? Go ahead and put it in the chat and we'll give you, if there's something pressing, especially if some people have the same question. Nothing coming in fast. Everybody's overwhelmed. You should be overwhelmed the entire time. Not surprising that this is overwhelming. Like I said, summer, way too fast. So good luck tonight. I think some of the GSIs have an office hour or something today even, so you can catch them. Like I said, the exam looks a lot like your homework and your chem quizzes. Review what we did today, look at the dinging noises, and that'll be your highlights. Other things? Okay, good luck tonight, guys. We'll see you tomorrow.